Well, welcome again to our journey into algebra and number theory. I thought we'd finish the quadratic reciprocity section with a little application to a very famous equation called the Bachet equation. The general Bachet equation looks like y squared is x cubed plus k, and it's an example of what is known as an elliptic curve. These are much studied and much work being done on them. Even at the present time, elliptic curves are a very important branch of modern number theory. This equation in particular generated a great deal of interest and research. It goes all the way back to Diophantus in 250 AD. Diophantus posed the following problem. He said, find a right-angled triangle in which the area added to the hypotenuse gives a square, while the perimeter is a cube. This was typical of the sort of questions Diophantus posed. It comes apropos nothing, it's just an interesting question to ask and turns out to have interesting solution. You want to find a right-angled triangle to which the area, you add the area numerically to the hypotenuse and you get a square number, while the perimeter is numerically a cube, a perfect cube. Well, what he does is he writes the shorter sides as 2 and a, and the hypotenuse as y squared minus a. So to look at a picture here, he writes the two shorter sides as 2 and a, and he writes the hypotenuse as y squared minus a. It's quite clever because the area then is a half the base times the height, which is a, and if you add that to the hypotenuse you just get y squared, which is a cube, and the perimeter is y squared, the a's cancel, the perimeter is y squared plus 2, and the point is you want this now to be a cube. So this is what he does. This is typical also of the kinds of trickery that Diophantus does in his solutions. So we've satisfied the first condition. We need y squared plus 2 to be a cube. So we're going to solve x cubed is y squared plus 2, which is similar to, which is the, I can rearrange to y squared is x cubed minus 2, which is the Bachet equation with k equals minus 2. Now, Diophantus does funny, amazing things that just happen to work. So what he does now is he puts y to be m plus 1 and x to be m minus 1. Why does he do that? Well, because it happens to work very nicely using symmetry here. You plug that in and you replace the y with m plus 1, replace the x with m minus 1, cube it all out and simplify, and write it in this form. You get m cubed plus m is 4m squared plus 4. Now what he does now is he just factors m out of this one, so you get m into m squared plus 1. He factors 4 out of this, you get 4 into m squared plus 1, and he cancels out the m squared plus 1 and just says m equals 4. Very clever. We then get y then as 5 and x as 3. And this in fact gives you a solution. In fact, y is plus or minus 5 and x equals 3 turns out to be the only integer solution to the problem. So earlier this century, Mordell proved that for every integer k, this Bachet equation, as it's called, can only have finitely many solutions. Here I'm just going to show that the equation y squared is x cubed plus 45 has no solutions. So the Bachet equation in this case has no solutions. And I'm going to do this using quadratic reciprocity. So working modulo 8, we can see that x must be odd. If x is even, then you can show modulo 8 that y squared is 5 mod 8. And that one is easy to show to be impossible. 5's not a square mod 8. So if x is so x has got to be odd. So that means if x is 1 or 5 mod 8, then you can plug that in and x is got to be 1 mod 4 then. If you've 1 or 5 mod 8, you've got to be 1 mod 4, and you plug that back into the equation, we get y squared is congruent to 2 mod 4. And that again is impossible because 2 is not a square modulo 4. And that only leaves the cases then that x has to be 3 or 7. So we showed it can't be odd, so it can't be 2, 0, 2, 4 or 6 mod 8. And it can't be 1 or 5, so all that's left is 3 and 7. So I'm going to firstly suppose x is 7 modulo 8. And we can then, I can rewrite the equation I started with, that's this equation here. And all I'm doing here is I'm going to write this as x plus 3 times something, and there's the something, and I get a remainder of 18. Now this number here, modulo 8, this is just minus 3. That's easy to check that in this case, if x is 7 mod 8, then you plug this in, you get minus 3. So if this factor here, it can be factorized, if this term here can be factorized as p1 up the alpha 1 up to pr to the alpha r, where all of these are primes, then at least one of the primes must be congruent to plus or minus 3 mod 8. Because this is minus 3 mod 8, and we see then that exactly one of the p's must be congruent to plus or minus 3 mod 8, because the product of all these primes gets you back to here again. So let p be such a prime factor. So p is a prime factor that's congruent to plus or minus 3 mod 8. Then modulo this p, this prime that we've got, this is 0, and so we get y squared is 18 modulo p. That tells me then that 18 over p, the Legendre symbol must be 1. I can take a 9 out of here and rewrite this as 2 over p. And we've seen before that means this p must be plus or minus 1 mod 8. But that cannot be because our p is plus or minus 3 mod 8. So that's a contradiction. Finally, we do a similar argument. If x is congruent to 3 mod 8, then we use this factorization this time. So I divide this by minus 3. I get a factor and 72. I now use exactly the same argument, which you might like to grind through and do. And again, we obtain a contradiction. And that means the original equation has no integer solutions. So that's just a little application of the quadratic reciprocity theorem to one particular case of the Bachet equation. And that's the end of our section on quadratic reciprocity.